Chapter 5 is Stereoisomerism, so that's what we're going to be covering here today. We're going to cover the parts of the first 4 sections in this lesson: overview and introduction to isomerism, designating configuration using the Kahn-Ingold Prelog system, and then optical activity. That's where we're going to end about halfway through that section. Isomers are any chemicals that have the same chemical formula, but a different order to the connectivity of the atoms, which would qualify as constitutional isomers, or they have the same connectivity, meaning the same atoms are bonded to the same atoms, but the placement or arrangement of the atoms or groups of atoms will be different in 2D space or 3D space. All right, giving an example here of some constitutional isomers. If I gave you the structure, let me leave that up actually, of pentane, which is going to look like this. Pentane has the chemical formula C5H12. If I move a couple of the groups off of there, I could have this structure, which is also C5H12, but it would actually be named 2,3-dimethylpropane. It has the same atoms, 5 carbons and 12 hydrogens, but they're connected in different ways. For example, if I number the carbons in pentane, there's 1, 2, 3, 4, and 5. And in the 2,3-dimethylpropane, 1, 2, and 3, and then 4, 5. You see 4 used to be connected to 3 and to 5. Now it's connected to 2. 5 used to be connected to 4, but now it's connected to 2 as well. So those are constitutional isomers. Stereoisomers, on the other hand, will have the same atoms bonded to the same atoms, but they're just going to look different. So here's an example of that. Let's say that this chemical formula, this is actually called trans-2-butene, and it'll be C4H8. There's 3 hydrogens here, 3 hydrogens there, 1 hydrogen here, and 1 hydrogen there. All right, so I could actually, I'll write CH3, CH3, and then the H's will go there. Now you can see that the carbons are connected through the carbon-carbon double bond in that structure. However, if I draw this, and now the hydrogens will be down there, and the 2 methyl groups coming off of the double bond don't connect through it like it did in the trans-2-butene. This one is actually called Cis2 Octane, but they have C4H8. They both have the same chemical formula. Looking at the carbon right here in red, we can see that that red carbon has a methyl group on both structures, a hydrogen in both structures, and it's double bonded to another carbon in both structures. In the same vein, I'll make it green now, that one on the right of the double bond. That green carbon in both structures is bonded to a hydrogen, a methyl group, and the red carbon. So connectively or constitutionally they're the same, but in 2D space they're different. Going back to things we talked about in the last chapter or 2 chapters ago, you can't convert between the trans or cis isomers of the double bonds, and that would be because the carbons have the parallel p orbitals, and those p orbitals have to be parallel in order to form the pi bond, which would connect them there. Remember, the sigma bond will be there. So any bit of rotation would get in the way of that. If I actually, let's make this not yellow, but Let's make it red. All right, we'll make that p orbital red, and then the pi bond here, I'll make an orange color because red. I know it's gonna look like this, and it's a highlighter, so it doesn't look great. But they're yellow and red are combining in the middle to make the orange. Maybe I could fix it like this. No, that didn't work. Okay, so you have that. If there was a rotation, though, we would get. I'm going to look at it from the side, and not. I'm going to look at it from that angle instead of from the side, I should say. So the front carbon, if I rotated around that sigma bond, would end up being like this. And the back one, which I don't know how yellow or blue got selected there, should be yellow. They'd be like this. And so they're no longer overlapping. They're not creating that pi bond. So you can't convert between the cis or trans isomers. You have to break the double bond. Then the rotation has to occur, and then they would have to align in the different form, and then the double bond would have to reform itself in order to switch between the two. In the same way, constitutional isomers can't just be transferred from one to another. Carbon-carbon bonds, in the case of the pentane and 2,3-dimethylpropane, they would have to be broken, and then maybe carbon-hydrogen bonds would have to be broken, and things just rearrange themselves and attach in different places than before. So they're different molecules, as constitutional isomers. These are different molecules as stereoisomers. And over here, it said just stereoisomers, and I just gave an example that, they are what they are. Here's just another set of examples: butane and isobutane, or what should really be called 2-methylpropane. Right there. They have the same chemical formula, but again, the connectivity is different. So just another term for constitutional isomers are structural isomers. On the right, we have the cyclohexane derivatives, cis1,2 and trans1,2 cyclohexanes. You cannot convert from the cis to the trans here. It is impossible. You have a hydrogen down here versus the hydrogen would be up, and the fact that the molecule is cyclical restricts bond rotations. So although these are sigma bonds, because they're rings, you can't cause any of these to rotate. That might cause a flipping of those two groups of atoms coming off of this carbon or that one. And so because they can't actually just freely rotate, now this one could freely rotate because there's nothing restricting it on the right end of it. So that could rotate itself, but with the three hydrogens there, they're just spinning around themselves. The carbon is always going to be up, while the hydrogens are spinning around like a pinwheel. So anyways, again, just when they're isomers, they cannot be converted from one isomer to another without breaking chemical bonds. I will mention that it calls these geometric isomers. That's a subclass of stereoisomers. Another slide. Now I'm breaking down the stereoisomers into different groups. What I had called geometric isomers, I now have as EZ isomers. We'll come back to that officially at the end of this chapter, not today. But you see there's cis2 butene again and trans2 butene. On the right, we have what are called enantiomers, and that's going to be discussed later on. But again, you can see we have the same groups, and that red carbon is going to have a hydrogen on both, a methyl group in both, and a hydroxyl group in both of those two isomers. But they are simply different molecules. You'll notice the hydrogen is in the back in S2 butanol, and it's in the front in R2 butanol. This carbon bond could rotate around, but if it did, and we wanted to put the hydrogen in the back and the methyl group in the front, like we have in S2 butanol, that would actually create this, where the hydroxyl group is down, the hydrogen would be in the back, and the methyl group would be in the front. Ignore the bond angle there, but that's how it would look. And so you can see no matter what, if I take this structure here on the left, it is different. The hydroxyl groups are not in the same spatial plane as each other, and so they're just different molecules, hence why we designate them differently. One is the S isomer and the other is the R isomer. Here's more examples of stereoisomers specifically with double bonds. There's the Cis2 Octane, and you can see we have that group and this group on the same side of the double bond, hence why it is cis. Whereas in trans-cinnamic acid, we have this whole group on the bottom left, and then this whole group on the top right, hence why it is trans. And just to point out, those are the hydrogens. And in the other one, the hydrogens are here and there. So those say cis and trans. This last one, though, does not. And it's because this carbon on the right side of the carbon-carbon double bond that is now with red there, it has two hydrogen atoms bonded to it. Anytime a carbon of a carbon-carbon double bond has two of the same group, that means that that double bond cannot be cis nor trans. It can be neither cis nor trans. And what we would do is say, well, compared to the group that I've highlighted in this faint orange, that hydrogen is cis to it, and this hydrogen is trans to it. So if it's both, because the hydrogens are the same, and we'll see the rules officially in a minute, but when they're the same, it's going to be neither cis nor trans, because there's no winner in a sense. All right. Section 2 is Introduction to Isomerism. Even though the last one was an overview, we now have it officially introduced here. Isomers, specifically stereoisomerism or stereoisomers, they have this property called chirality, which the word chiral in Greek means handedness. If you think about your hands, you look at them, if you point your thumbs to each other, you're forming mirror images. They're the same basic shape, but my left hand has my thumb on the right, my right hand has its thumb on the left. They're different. If I were to take my right hand and put it on my left arm, it would look weird and it just wouldn't work. And likewise, if I had switched places with my left hand and right arm. And so we call this, for molecules that have that feature, like I showed in an earlier slide, we call that chirality, handedness. In other words, like for my left hand, I could only put my left hand into a left-handed glove and it feel comfortable. Yes, there's gloves that are made that are themselves not chiral. You could put either hand in. Think about in the laboratory, those like latex or nitrile gloves are meant to fit either hand. It doesn't matter. So they're made to be what's called achiral, which actually means something that is not chiral. It has no handedness. All right. Another example would be like shoes. You have a left foot, it goes into a left shoe. If you put the right shoe on your left foot, it would feel uncomfortable. Even your t-shirt is technically chiral. If you put your shirt on backwards, you probably notice it doesn't feel right and you switch it. Even if it was, unmarked, it was just a plain white t-shirt, they make the back of it, the like neck hole, different than the front of it. And so you feel that difference and it feels uncomfortable and you usually switch it around. Now, not everything is chiral, obviously. Just looking around my room here, I've got Post-it notes. A Post-it note is just a square, and it itself is achiral. Actually, a better example would be like a CD disc that you put into, or let's say a Blu-ray disc. You put it into the Blu-ray player. It's a disc. It's a circle with a hole in the middle. And it doesn't matter how I orientate it in the disk drive of my Blu-ray player. It'll still deposit into there and it should function with no problems as long as the disk isn't scratched. So that would be an example of something that is achirality. And the molecules that have three-dimensional different arrangements of atoms in space will be themselves chiral most of the time. So if I'm going to add something here, molecules or isomers can be chiral. I wouldn't talk about the double bonds, the cis or trans, as being chiral because they're not what we would call mirror images of each other. Okay, so when we're talking about like chirality with the hands and handedness, if like I had mentioned, if you put your thumbs pointing towards each other and your hands, out, they're forming mirror images of each other, and that's what is going to cause things to have chirality is when they're mirror images. But again, these two structures are not mirror images of each other, so they will be achiral. Let me erase those again. All right. So superimposability here is that chiral molecules are those whose mirror images are non-superimposable. That doesn't actually define superimposability, but what it means is that two images, if they don't overlap when they're mirror images of each other, then they will be chiral. If they do overlap, then they will be achiral. So let me give you an example of superimposability. If we have this chemical here, which will be 1,2-dimethylcyclohexane, and I make a mirror image of it, you'll see, let me rotate it around, that these two molecules are mirror images of each other. But all it takes for me is not to do that. All it takes for me, it's not. All it takes for me is to rotate, okay, we have that there, is to rotate it around, and you see that it's the same molecule. So if I rotated it around and then overlap it with the first one, you see that they are superimposable on each other, and therefore this molecule is achiral. But if I take another molecule, let's have it. So this would be the cis isomer cis 1,2 dimethyl cyclohexane. If we take the trans isomer of that, then the mirror image of it, which now I'm just going to draw, the mirror image of that structure would look like this. And if I rotate that around, you'll see that it does not properly overlap with the other one, because this group is above the plane of the screen, this one is below it, and vice versa for the bottom methyl groups. So they don't overlap. So these are non-superimposable mirror images of each other, and therefore these are going to be chiral molecules. Chiral centers are atoms that cause or can cause a molecule to be chiral. And this occurs when the atom has 4 different groups attached. Now, it doesn't always mean it's going to make the molecule chiral, but it likely can. So if we look at the molecule here, the cis isomer, all right, this carbon in now blue has a hydrogen. It has, whoops, a CH3 up there. It has that, which I'll write is a CH2. And it has this, which is not a CH2. There's one hydrogen here, plus that methyl group, plus this carbon over there. And then the CH2 also had that carbon. It's different in those 2 different directions. So this is a chiral center, which we typically indicate with asterisks. Also, this one is going to be a chiral center because it has a hydrogen, a methyl group, this group over there, and then this group over here. They're structurally different, all 4 of those groups. And so you have 2 of them. There's 2 chiral centers in that molecule. However, the molecule itself was a chiral, and that is due to something that we'll talk about later. When we look at this, we have a chiral center there and here again, but because the mirror image was different, they are chiral molecules. So it depends. You're going to have to look at these molecules carefully and figure out, sometimes 2-dimensionally and sometimes 3-dimensionally, what's going on. Do these mirror images overlap? Are they superimposable or are they not? Here's some more examples. The gloves on the left are chiral because they are simply mirror images of each other. In the middle picture, those vases or glasses would be achiral because they're mirror images of each other, but they're literally the same thing. So there's no difference in either side there, which makes them achiral. The shoes on the right, again, are going to be chiral because they're mirror images that are non-superimposable. And let me show that with the gloves. If I take the gloves, you see the thumbs in the gloves here, they're pointed in different directions, so they're not superimposable. It's actually perfect the way I showed that. And same with the shoes. You have the inner portion of the left-footed shoe like that, and the other one would look like this, and they're just not superimposable on each other. The molecule here, as you see, that carbon in there, the black one, would be a chiral center because they're mirror images as shown, and they don't overlap with each other. All right, you see the blue is facing in the opposite direction as the white and the green, or not the opposite direction, the same direction in those two different molecules. If I were to spin this around, and I can't really do this very well in this program, this is something you should have a model kit and just do. But if I take this object and I flip it, it looks like it's the same thing. But if you actually flipped the three-dimensional object in real life, well, what you have here in green would no longer be in front, it would be in the back, and the white one, which was in the back, would flip around to be in the front, and so it would look like what I've drawn there. And you can see, because the green and the white aren't in the same space as each other, although the red and the blue are, these are different molecules. They are therefore chiral molecules. I can't rotate it any other way. It'd be nice if I could do that. All right, so when we're looking for chiral centers, you need to look for 4 different groups. So in this molecule, you have to remember the implied hydrogens. Here's an implied hydrogen. So this carbon has a hydrogen, a chlorine, a carbon, and a carbon. But again, those 2 carbons are not equal. This is a different group than the green one. Let me use a different color right there. Let's make that yellow. The yellow one is a different group than the green one, and therefore that molecule will be chiral. The mirror image of this molecule would look different. You'd have a different 3-dimensional arrangement. If I just make a copy of it here and I flip it over, let me give myself more space. Just remember that I made an actual physical copy. So what I'm going to do is not really right, but if I take this copy and I flip it over to make it a mirror image, it's now a mirror image, okay? But when I flip it back to have the greens and yellows in the same like space as each other, so again, right here is this is the mirror image, okay? When I flip it over now, the chlorine that was in the front should go into the back. Like now it would have the dash bond, okay? And the hydrogen would go in the front. And so you see those are not overlapping properly. They're different molecules. They're chiral molecules, therefore. That's always the case. If you have 4 different groups of atoms bonded to any atom, that atom will be a chiral center. We're going to mostly look at carbons here because carbon forms 4 bonds, nitrogen 3, oxygen 2, hydrogen 1. So for the most part, it's just carbon. We'll call them chiral carbons. We look at this group here, or this molecule here, you see that group is different than this because there's 2 carbons versus 3. There's also a hydroxyl group, and then there's a hydrogen in the back. If you look at 1-bromo cyclohexane, this has a hydrogen in the back too. But if I go to the left, or if I go to the right off of this red carbon there, they're both CH2s. So you would theoretically go to the next carbon. Let's make it yellow and orange. And again, they're both the same. They are CH2s. And then they meet in the middle. And so therefore, it doesn't like really the left side of that red carbon and the right side are the same. And so this molecule is achiral. When we look at the structure over here, though, if we go to the left or to the right, we have a carbon there with two hydrogens, but we only have one hydrogen there, versus actually, like if I drew everything connected to that highlighted one, there's two hydrogens and a carbon, versus on that one hydrogen and a carbon. It's different. In fact, what they do when there's double bonds is they treat that double bond as if it's going to two different carbons. You treat it like two singly bonded carbons there. And so you make this connection like, yeah, there's a carbon and there's a hydrogen on each, but we have a difference of a carbon and a hydrogen there. And so this atom here truly is a chiral center. When molecules have chirality, and there's multiples of them that are mirror images that are non-superimposable, we call those enantiomers. So these are isomers that are non-superimposable mirror images. And I'm going to add here, and they are chiral. So if you look at the two molecules there, they're not mirror images as shown, but if I were to flip the molecule on the right over, let me do that, then again, because I've flipped it, that actually makes the methyl group there go from being in the front to being in the back. And so they are mirror images of each other, but they're non-superimposable. And because in here, in this way of being drawn, the methyl group is up in the one I'm moving around, but it's down in the other one. So in 3D space, they're aligned differently, therefore these are enantiomers of each other. Section 3 here is designating configuration using the Kohn-Ingold Prelog system. All right, so this is how we're going to officially name enantiomers. All right. The first rule is to prioritize all four groups connected to the chiral center. The chiral center in these two different, although similarly structured molecules are here and here. Okay. We have it says to follow the point of first difference rule. The point of first difference rule states that you pick the atom with the highest atomic weight. All right, as priority 1. All right. And in here we have a hydrogen, a chlorine, an oxygen, and a carbon. So by atomic weight, the chlorine wins. Next is going to be the oxygen, then the carbon, and then the hydrogen. We just pick them in order from heaviest to lightest. All right. On this structure, though, we have a carbon and a carbon, a hydrogen and a chlorine. The chlorine is still the heaviest, so that's number 1. The hydrogen is still the lightest, so that's number 4. But we have 2 carbons to compare. Notice these are different groups overall, and so this is a chiral atom. But what's going to happen here is we have to follow the point of first difference. So this is officially what we're talking about here, this point of first difference rule. And so what we're going to do is we're going to say these carbons effectively cancel each other out. But then we have, coming off of those, we have these hydrogens and those other carbons. So there's a hydrogen, and a carbon. a hydrogen, and a carbon coming off of these carbons themselves. Well, they're also the same. You want to like compare them and cross out. When you find that first point of difference, then you pick the winner. Well, off of the blue carbons, the one on the right has 3 hydrogens, H, H, H. The other one has 2 hydrogens and a carbon, HHC. So you can see these hydrogens cancel out, those cancel out, and then you have a carbon versus a hydrogen, and that means that we have group 2 will be over here, and that will make this group 3. The shorthand for the point of first difference rule is if the chains are linear, go for the longer chain. That's always going to work. But these chains could be branched, and that's going to affect things. So if I had my chiral center here, let's say there's a hydrogen there and a chlorine here. Whoop, that's kind of messy. Let's have that, and then we have this. All right, so the carbon here, we're going to do it by color. Those two are both carbons, all right? So carbon and carbon, they cancel out, all right? The next stage will be, I'm in blue here, and so we have a carbon right there, and this has 2 carbons. What's missing, obviously, are the implied hydrogens. So in blue, there's a hydrogen, a carbon, and then a hydrogen, carbon, carbon. The hydrogens cancel, a carbon cancel, and we have a hydrogen versus a carbon. So the right side wins. This chlorine was 1, the hydrogen 4, and we have 2 and 3. If we look at this structure more carefully, you'll notice that the group to the right, if I take this off, I could call that an R group and call this an isopropyl group. And that's got a C3H7 chemical formula over there. More importantly, it has only 3 carbons. If I look at the left side and I group all that together, well then it's actually like this, and that is an isobutyl group, and that has C4H9. It's got more carbons and more hydrogens. It's a bigger group, but it's lower in priority here for the Kohn-Ingold Prelog system because we have to follow arbitrarily the point of first difference rule. Okay, so it's not only size of the groups. It is size of the groups if they're unbranched. When they're branched, like these two were coming off, you have to follow this point of first difference, going step by step, every atom coming off until you find a difference. And then at that difference, then you're picking the atom of highest atomic mass. All right, so I've numbered them as in the previous slide here. It says rule 1AI is that double bonds count as separate single bonds. I already mentioned that. So if I were to give a structure, we saw this already, like that, the hydrogen would be in the back. That's going to be group number 4. The bromine is group number 1 because that weighs a heck of a lot more than the carbons. We have a carbon here, a carbon there. So technically, those carbons cancel out. In the next stage, there's a hydrogen and a hydrogen and a carbon. And over here we have a hydrogen, no, we don't. We just have one hydrogen and a carbon. But we're going to do hydrogen, hydrogen, carbon, hydrogen, carbon, carbon. Hydrogens cancel, carbons cancel. So you're comparing a carbon versus a hydrogen. The carbon wins, which means it's the right side with the double bond. And so in this structure, this would be 2, that would be 3, and there you go. Let me put that in. Just to make sure we're entirely clear, if there were double bonds on both sides, then it would be the same. It's symmetrical going counterclockwise and clockwise, so it makes no difference. And that means this carbon here would be achiral. Rule 2, if necessary, rotate the molecule so that the fourth priority group is on a dash. So these were the structures we were given in the previous slide. And you see the hydrogens are on the wedge bond, not the dash bond. So after flipping it over there and here, now the hydrogens are in the back in both of them. That's the next step. And there's a reason why it's preferable. You could technically have it above or below. Like you want the lowest priority group, the fourth one, to be either on a wedge or a dash, but it's sometimes actually better to have it on a dash. All right, and so rule 3, now the two molecules have the hydrogens on the dash. Determine whether the sequence 1, 2, and 3 of the groups are clockwise or counterclockwise. In the left molecule, it's going counterclockwise. In the molecule on the right, they're going clockwise. Clockwise is going to be called R, while counterclockwise will be called the S enantiomers. So again, we had 1, 2, 3. This goes counterclockwise. So that's now officially going to be the S isomer. And the other one was 1, 2, 3. And so that was the clockwise one. And so that's officially the R isomer. Now, there are the names here, S3 chloro-3-ethoxypropane and R-chlorohexane, which is actually named wrong. So it actually should be R3 chlorohexane. My bad. But we haven't gotten to naming molecules that are not alkanes yet. So we don't really need to focus on what all of this stuff means or that. Just know that we're calling that S and that R based on being clockwise or counterclockwise. Now the R in the R isomers stands for rectus, which is Latin for right. And the S is Latin for sinister. Let me make sure that's spelled right. Sinister. No, it's just sinister. And this actually sounds like it's evil, but turns out the word sinister actually comes from left because they used to think that people who were left-handed had some evil bewitchments, I guess. And I should make this, there we go. So S stands for sinister or left. Again, now what you want to do, yes, it's counterclockwise to the left. But if you take your left hand and you point your thumb in the same direction as this hydrogen, your fingers will curl counterclockwise, just like that. So that's why it is S or sinister or left. Whereas with R, if you put your thumb down in the direction of that hydrogen, your fingers will curl in the clockwise direction, so you're using your right hand to connect the other two, and we're ignoring the wedges there. We're just doing them this way, and so that's going to be the rectus or right. So I'll add, after just looking this up, that rectus actually means straight, but it means straight in the sense of straight up and down or straight line. And so it kind of comes from building materials where we'd call this a right angle. And it's the right angle when it's 90 degrees. And so rectus actually means straight, like this is straight up and down, but they formed that right angle. So it's not officially right, but it works good enough there. Whereas this is true. If there are two or more chiral centers, each configuration is preceded by a locant or locant. And so you see here, we really, at this chiral center, the OH is 1, this group would be 2, and that would be 3. The hydrogen is in the back, so you use your right hand, and so this is an R configuration. When we go to the other chiral center, which will be right here, we have a CH3 group there, so there's a hydrogen up here. And then identifying the groups, well, that'll be 4. We don't really ever need to worry about the 4. But, well, what I'm going to do is do green. We have a carbon, a carbon, a carbon. Let's call this carbon 1, carbon 2, carbon 3. 1, 2, and 3. Coming off of those, let's do some purple. We have a hydrogen, and a carbon. We have 3 hydrogens. Oops, and I messed up the other one. There we go. And then for 3, we have a hydrogen, an oxygen, and a carbon. So they all 3 have a hydrogen. Then you want to go for like the lowest. So hydrogen, and then really that's I guess a carbon. So that means the left side with the C3, this is going to be group 1. All right. So we don't need to worry about the rest of it. And then between C1 and C2, it's a hydrogen versus a carbon. So carbon 1 wins, making that 2, and that is 3. Now the hydrogen is up, so point your thumbs up, and you'll see your left hand with the thumb up goes in the clockwise direction there, and that's why this is an S isomer. So 2R, 3S. If I get rid of the mess now, we can just put R and S at those positions. Numbering the molecule, it would go 1, 2, 3, 4, and 5. So that's why it's 2R and 3S. There's a methyl group at carbon 3. This OH is at carbon 2, and there's 5 total carbons. So 2R, 3S, 3-methyl, 2-pentanol would be that structure, or that structure's name. Make sure you put the locant, then the configuration there. These letters are italicized, they're also capitalized. 2R3S. Now name the following molecule, including stereochemistry. Now this molecule is an aldehyde, and we haven't learned how to name aldehydes. But what we'll see is that the aldehyde has to be a part of the longest continuous chain of carbons. All right, so if you said we have 1, 2, 3, 4, 5, 6, 7 as the longest chain, you'd actually be wrong. It should be 1, 2, 3, 4, 5, and 6, because that includes the highest priority functional group in the molecule. And obviously, we'll get into those later throughout this organic chemistry course or even next semester. But that is the official way to do it. We don't really need to worry about it so much. Really, the key thing is this is the chiral center. Is it R or S? Well, we have a CH3 here. We have a carbon. So let's do that. We have a carbon here. We'll call this 1, and we'll just go 2, 3, and 4 around. That's not the official order, though. So we'll have C1, C2, C3, and C4. Then we have an oxygen it's a double bonded, so oxygen, oxygen, hydrogen. At C2, there's hydrogen, hydrogen, hydrogen. At C3, there's those two hydrogens and a carbon. At carbon 4, there's two hydrogens and a carbon as well. So you can see that the aldehyde is priority number 1. So we can, because there's the oxygens there coming off of it. So that is fine. The next one, you can see C2 is going to be priority 4 because all 3 of them are hydrogens. So this is 4. And then the other 2 are the same. Hydrogen, 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 carbon, carbon. Well, going off of those, we have hydrogen, hydrogen, and carbon versus hydrogen, hydrogen, hydrogen. So that's going to be 2, and this will be 3, because those cancel, and then you're comparing a carbon to a hydrogen. So this is group 2, this is group 3. Now if I get rid of some of the mess here, I'll just rewrite the numbers. We have 1, we have 2, 3, and 4. So now your thumbs want to point up because group 4 is up. And so in this case, if you have your left hand, it'll go in that direction. So this is going to be S as the configuration. All right, now the numbering of the chain would actually start at the aldehyde, so it would be 2, 3, 4, 5, and 6. We have a methyl group at 2 right here. We have an ethyl group at carbon 2 as well. There's 2 ethyl, 2 methyl. And so the name of this molecule would be S2-ethyl, 2-methyl, and it's hexanal because it's an aldehyde and the longest chain is 6 carbons. All right, physical properties of enantiomers. So a key thing here is that enantiomers have the same physical properties except optical activity. They often have different chemical properties. But they can be the same. That's for enantiomers. You look at the examples here There's R carbone and S carbone. You see that the melting points are both 25 degrees Celsius and the boiling points are 231 degrees Celsius. Carvone is the chemical responsible for the flavor of, like, well, it has two distinct flavors. One enantiomer actually tastes like caraway seeds, which maybe you know that. You can go buy that at grocery stores as an herb or whatever. It's usually added to breads for rye bread. And the other one is responsible for the flavor of spearmint, which is crazy. And actually, it's the R carvone that is the spearmint, and the S carvone that are the caraway seeds. So if you've ever had rye bread, those seeds in there are caraway seeds, and they have that S carvone chemical in them that's giving them that flavor. But those two different things taste totally different, so they're chemically different because they're interacting with enzymes in your taste buds or receptors in your taste buds, but you're essentially physically the same. However, this section is optical activity, so the key thing will be that as far as physical properties are concerned, they're the same except that optical activity. But what is optical activity, you might be asking? Optical activity is the ability of a chemical to rotate plane polarized light. Well, what is plane polarized light? Okay, light, also known as electromagnetic radiation, is an oscillation of perpendicular electrical fields, or really electrical waves, and magnetic waves. All right, so light, visible light, or any other type of light, ultraviolet, infrared, etc., they are a superposition of both of those waves that are propagating from some source to wherever they're ending up. They're going up and down, and those are repeating at equal increments. And the magnetic and electrical fields are perpendicular to each other in their oscillations. But overall, light is the combination of both of those. As a result, and this is, if you download the PowerPoint for this, you'll actually see that these are GIFs, and so these are moving. Light is actually a superposition of these going in the right-hand direction. So in the GIF, there's this arrow. I'm going to make white here. Give me a second. This arrow here is actually rotating clockwise around these peaks. And basically, you're seeing these helices moving to the right direction here, and that arrow through that process is moving clockwise. So this is light that's moving in the right-hand direction because it's clockwise. In the other picture, the arrow is moving in the opposite direction. So it's moving counterclockwise, which is the left-hand direction. When we receive light from the sun, for example, it's actually, we typically just draw waves like, nice, consistent oscillations like that. But that's an oversimplification, right? Just really looking at the electric field or the magnetic field, and it's really a superposition of both, which is where the coiling or the helical nature of these come from. But But that's even still an oversimplification where the light we're receiving from the sun is actually both right-handed and left-handed. And so it's a superposition of both of those, which is kind of crazy, but that's still not plain polarized light. These are spherical, helical polarized light. All right, plain polarized light is when, if itself officially, when light gets artificially polarized into a plane. Okay, meaning not an airplane, but a flat sheet. These are helical. They're not flat, and even that's, whatever. It's up and down. So this is what it's trying to show. We have some source of light. Here, this monochromatic light. Usually this is going to be sodium lights that's used to make the studies for these chemicals. Okay. Yeah. So when you take monochromatic light from a sodium lamp, or it could be light from the sun, which is omnichromatic, has all the colors. It's again coming to you in both directions as it's coiling. That's what this middle part there is trying to showcase. Light is coming at you at every angle that's possible. But we put a polarized filter in between that light and a sample tube containing the chemical. You see that this polarized filter is essentially gratings, a grate, and light can only pass through that grating in one direction. In this case, it would be like up and down. So light could pass through that vertically, but it's essentially creating this plane. I know I'm making it 3D, but it's a plane that's going to pass through that filter, and then that light is going to hit this chemical inside of a sample tube. Since the light has been polarized by, or should say plane polarized, it's going essentially just up and down through it, it's going to hit this in that same direction always. If the chemical has optical activity, it will rotate it either to the left, like we see over there at the end, what's going to be in the negative direction, or it could rotate it to the right, which would be the positive direction. In the picture here, it looks like they're showing it rotating to the left. And so that's just going to have a negative rotation. We can measure the amount of the rotation in a polarimeter, which has a second filter. If I take the second filter and it is in the same orientation as the original one, what you're going to see is nothingness. It'll be complete darkness coming through over here. All right, and because it's vertical like the first one, but the light has been rotated counterclockwise. Okay, if you then take your polarimeter and you rotate the filter, I know like it's not the same, it's a circle, so it wouldn't actually do this, but you could just rotate it until you see the light, and you measure the angle between what it was vertically and to what it is now, and we measure that, and that measure of the angle is that chemical's optical activity. When we're comparing samples and their optical activity, we want to make sure the length of the path for every sample is the same. All right, the length of that tube. There's also going to be a consideration for the concentration. And so there's also temperature and yada, yada, yada. We got to follow standard conditions in order to make good, fair comparisons between every chemical and their optical activity. So just as a reminder, standard temperature is 25 degrees Celsius or 298.15 Kelvin. Standard pressure is 1 atmosphere. Standard concentration is 1 mole per liter. All right. So the concentration of the sample should be 1 molar. The pressure around should be 1 atmosphere. The temperature 298.15 Kelvin. And then the path length here, L, is going to be 1 decimeter for the tubes, which is 0.1 meters in length. So those are the standard conditions in these polarimeters. Now, the key thing is that chiral molecules rotate plane polarized light, while achiral molecules do not. All right. So again, if we had, just to make this simple, this compound we determined was achiral. So this is not going to rotate light. If we have this chemical, this one is chiral and it does rotate plane polarized light. This molecule will be achiral and not rotate plane polarized light. Then when we look at, let's go back to the carbon structures. Right there. That's the R carbon. The S carbon will be the other. And one thing to notice here is that this molecule has 1 chiral center, or both of these only have the 1 chiral center, because they have to have 4 different groups attached. The carbon here has 1, 2, and 3 different groups. So double bonds will never be included in chirality. They just can't. Again, we would treat this as 2 carbons coming off of it that are also bonded to this carbon, which are also bonded to that. They're the same thing. So it has to have 4 different groups. This one only has 3 there. And so this has that, the carbones only have 1 chiral center to worry about. All right. The R carbon rotates light to the left, and we call that a minus. Well, I'll put minus here as far as counterclockwise. So a key bit of information here is that they will do it opposite. Always. One isomer will rotate light to the left or counterclockwise, and the other one will rotate it to the right, which is clockwise. Always. And the optical activity of these chemicals are negative 61 degrees and positive 61 degrees. So they have the same magnitude, the same amount of change in the angles, but in opposite directions. All right. So that's always going to be true for enantiomers. As long as their concentrations are the same and their path lengths are measured at the same and temperature and all that stuff are kept constant, then we get the same angle of rotation but in opposite directions. Let me do one more compound. If we have this chemical, again, it's got 2 chiral centers, but because the mirror image of it is the same molecule, it is a superimposable mirror image. Again, this one was a chiral. It's not going to rotate plane polarized light. The reasoning for why chiral molecules do and achiral molecules don't, regardless of if they have chiral centers, is a little difficult to understand. And I'm going to post a link to a video that shows that better than I can explain it. That'll be it for today's lesson. So I'll see you on Tuesday. Take care.